It's a great pleasure to have Melanie Köhler here as our speaker. Yesterday, she did her PhD in Münster in 2006, and then also did a postdoc there. Then she went for a postdoc to Columbia, Missouri, from 2008 to 2010, where she worked at IBE. And then went to Paris to IAS in 2010 to 2015, working with Ant Jones and on various different topics, all related to dust somehow, but in various applications of astrophysical dust. And is now on a Melanie Koehler fellowship in Queen Mary in London, working with Richard Nelson, where she's also now applying her knowledge on dust to protoplanetary disks. So today she will talk about two different topics, both related to dust, one in interstellar medium, and then her new work on protoplanetary disks. So let's welcome her here to Heidelberg, and look forward to the talk.
Thank you very much. So as Chris already said, I'm presenting maybe two topics. They're both on dust, but in two different environments, so in the interstellar medium and in protoplanetary disks. And the outlook of the talk is that I will give a very brief introduction, but I think I do not really have to say what dust really is in this colloquium here. So the first part on the dust in the interstellar medium is like a new dust model I want to present. I worked on with Anthony Jones in Paris and Nathalie Bizarre. And also not only in the interstellar medium, but also in dense regions where we see evolution of dust particles. The second part is dust in protoplanetary disk, where I mainly look at the dynamic state and a little bit of dust evolution. So very quick introduction. So well, dust is seen everywhere. It's brilliant. There's nearly 1% of the total mass is out of dust. It absorbs the stellar radiation. It heats the gas. And it traces in lines like the interstellar and interstellar interaction. So my work in general is towards a more realistic dust model, and I look at the evolution of dust from the diffuse interstellar medium to deadly disks. These are some pictures where you can see dust in various environments. In here? Okay, sorry, should I do the switch out? Better? Yeah. Okay, just like a small picture here of the Horsehead Nebula, IC484, where we see Horsehead Nebula, where I see the Horsehead here, very dense dust cloud radiated by this by the central star here. And this dust then eventually forms, or dust in general from the interstellar medium. We have the diffuse regions and the dense regions, where it forms like filaments, and eventually in clouds like this can also form protoplanetary disks. But we do not only observe in the visible, we have like, this is for example the Horsehead Nebula here in the infrared, and the Iris Nebula in the optical, but we look at a lot of different wavelengths to get information of how the dust evolves, how the dust looks like, so we have a spectrum where we can get information about the dust. So yeah, the first part was our new THEMIS dust model, where I worked with Anthony Jones and Nathalie Bizarre from the IAS in Marseille. So the new dust model looks like this. We have like, in the diffuse interstellar medium, we divide into three types of dust, where there are amorphous carbon dust particles and amorphous silicate type particles. We divide the amorphous particles into very small grains and into larger grains, and the silicate grains are mainly only large, 100 nanometer in size. I'll show the size distribution later. The colors here, so we have this very black color and we have the gray color. So we distinguish between aliphatic-rich and aromatic-rich amorphous carbon. Aliphatic-rich means you have a lot of hydrogen still in the amorphous carbon structure, and aromatic-rich means that a lot of the hydrogen is away from the carbonaceous structure. And this can happen due to radiation, which can hit the particles and kick out the hydrogen, and therefore it aromatizes the amorphous carbon. So that means all the small particles should be aromatic rich, while the larger grains should have a core which is still aliphatic rich, but the mantle can be aromatic. And for the big grains, we also assume a mantle of aromatic rich amorphous carbon, which can come into accretion processes, or perhaps already due to the coagulation of these very small grains on the surface of these dust particles. Now into denser regions in the molecular cloud, we have accretion process here, which is once the accretion or coagulation of these very small grains on the surface of the dust particles, and also accretion of the mantle on the surface of the dust particles. And if the environment, like in a molecular cloud, is relatively dense or dense enough that the radiation is not super strong, this material which accretes here on the surface can stay aliphatic rich. So there's not enough energy to really kick out the hydrogen, but it stays here, so we have like an aliphatic rich core, mantle on the surface of these particles, which can happen for these both kind of particles. And then eventually the particles coagulate into aggregates, forming the structures, and when the environment is dense enough, ice mantles can form on the surface of the particles. So this is our new dust models, including the evolution of the dust particles. And well, people might say, oh, again, a new dust model, but what is new in this dust model is we only use optical properties based on laboratory data. So we do not use astronomical silicate, we do not use graphite. We clearly have these new optical properties of aromatic to aliphatic rich amorphous carbon. We use the laboratory data of amorphous silicates as well. Another thing, this I will show later, so we have size and surface dependent hydrogenation or aromatic to aliphatic rich optical properties. And we assume that these amorphous silicates have inclusions. These inclusions could be iron or FeS nano-inclusions. And we did this because it was assumed that there is a depletion of iron and sulfur in the interstellar medium. And we included these inclusions in the silicates and see what influence it has on the properties. And then we have this core mantle particles which can eventually evolve into aggregates. So we have the evolution of the dust particles. This is the size distribution we assume. So we have for the silicates, we have a log normal distribution with a maximum at around 100 nanometer. For the small grains, small carbonaceous grains, we assume a log normal, which goes then for the larger grains into a power log, which goes then for the larger grains into a log normal distribution. And I think the rest I said already before. The calculations, so to derive the optical properties, which we need to get the spectral energy distribution, we use the VH code model, which is a theory-based code from Bowen and Hoffman, which is relatively quick. We can calculate like up to large grains very easily, very simply, which is very nice. And these are the results we get for different observations. So we have here the UV bump, we have the infrared extinction, we have the albedo and the SED here. So we can clearly see we can describe the UV bump very well. The extinction here, I should say. We use two different types of silicates. We use olivine and pyroxene type silicates, and since the peak is tiny bit shifted, we get actually a little bit broader feature. We get the albedo is explained relatively well, and here the SED was our main concern at the beginning to plot the SED. We see here the aromatic features and which are due to stochastic heating of the small grains, and we see the grains which are in thermal equilibrium here. Then, when our model was actually done, we got observation of the SDSS. So here's the EB minus V plotted versus the optical depth at long wavelength. And we see our model is the blue one, and it really fits. So that was really nice. We were really happy of this result. While the other models, like the companion I model, is another dust model, it didn't fit, and the drain and V model is about here, so Planck data ourselves, but what we got was an estimation of the temperature and of the spectral index. So what is done when particles in thermal equilibrium, you can fit the SED with the modified black body, which is shown here. So what you need is like this index, the spectral index here, which is the slope at long wavelength, and the temperature, which is mainly determined by the maximum of this SED. So observations with Planck were analyzed with this modified black body. So what we got were like, for example, this beta versus temperature plot here, or the luminosity versus temperature plot, or other observations. But what we saw that the model we did at the beginning from this old data fit about here, which is not too bad, but in general, well, I think we can do better. So our idea was then, we are not fixed. We never fixed the size of the mantle. So the mantle can vary, for example. The inclusions can vary inside the abundances we have. And also the size distribution of the carbonaceous grades can also vary. So we allowed to vary all these properties in reasonable numbers. And what we got was this at the end. So the dashed area here in pink shows the results we can obtain by varying these properties. So we see, allowing for little variations in the dust particle properties, we are able to explain these observations with Planck relatively well. That means we can explain the dust in the diffuse interstellar medium. So this is only the diffuse interstellar medium. And then there are observations when we go away from the diffuse interstellar medium and go into the denser regions of the disks. So we see here, for example, for the Orion A molecular cloud. This is the density plot. So we see we go from the diffuse interstellar medium into a denser region here where it's getting red. And the temperature plot here, the scale is inversed. So we see that the temperature here is getting colder while entering into the denser regions. Here the column density versus the emissivity at 250 micrometer is plotted. And we see when we go into the denser regions, we see that this emissivity increases. These two observations with Herschel and observations with Planck additionally show, here's again, this beta and the temperature plot. And we see again when the temperature is decreasing, so going into these denser regions here, the temperature is decreasing and the emissivity, the index here is increasing. That means the slope at longer wavelengths gets deeper. So that was the question, where does it come from? Why is it happening? Is it because there are radiative transfer effects going into the denser regions? But this was calculated and couldn't be neglected. Is it due to the fitting procedure? That was the big question. Is there degeneracy between beta and the temperature when I plot with a modified black body? Is it due to calibration effects? For Herschel, for example, in the PSF? Or what I like to show here today, is it due to changing dust properties? So I show here a little movie what we assume happens. So I showed this in the first plot, but these dust particles, we have the coagulation and accretion, then we have the coagulation of the larger grains forming aggregate, and eventually the ice mantle formation on top. And the dust particles I calculate look exactly like this. So four monomers combining together, where we have like from the abundance of the material, we have like 3 silicates and 1 carbon ring. We have these two mantles, the first one, the aromatic ridge, the aliphatic ridge, and then eventually the ice mantle. The problem with this, it sounds pretty nice, the idea. The problem with this is we have to calculate the optical properties for all of them. As I said at the beginning, core mantle particles is relatively easy. Can use the BH code, whereas the BME theory code relatively fast. And then when we come to the second mantle, so this core mantle grains, we already have to go to the discrete regular approximation. And in order to explain or describe these really well, we need a lot of dipoles forming one grain, so we need a lot of calculation time to do these calculations. And the same is for the aggregates without ice, so we call it AMM, and for the aggregates with ice, we call it AMMI. And in total, where we also calculated this for size distribution, it's not only one size, but this is the size distribution of the grains before, where we can calculate very fast, very simple. And this is for the core mantle grains, for the aggregates without ice, and for the aggregates with ice. The cutoff at the shorter is like a natural cutoff because the particles cannot be bigger. But here, the cutoff here at longer wavelengths is just the cutoff of time because the computations are the calculations are computationally so expensive that we cannot go to larger grains. But we have the peak, so we are in a very good range to do the calculations. And to just get these optical properties for these grains took about 2 years just for the calculations. Oh, well, I show the calculations quickly in 4 slides. And what we did, so we calculated with these programs I said, with this discrete dipole approximation and Lie theory, we get the absorption coefficient, the scattering coefficient, and the asymmetry parameter. And then we use a code called LASM in combination with the interstellar radiation field to calculate the spectral energy distribution. And here they are. So the black curve I showed before is for the standard grains, core mantle grains. And then when we add the second mantle, we got to this green curve here. So we see the add material, so the entire emission increases. But we can also see that the slope changes. It gets steeper. And this is due to the addition of the aliphatic-rich amorphous carbon, which has a steeper slope than the aromatic-rich amorphous carbon. And this is why we see this change in slope here. When we go to aggregates, we coagulate the particles and make them a bit bigger. Bigger particles always mean colder, so we get a little bit of shift at the shorter wavelength. But no other change in the beta here, no other change in the slope. And eventually, when we add ice, we again add material, so the entire emissivity increases. Particle gets slightly more colder, not that much. And also, again, no change in the material composition because water ice doesn't have a contribution to the slope here. Yeah. 2 years shown in 4 slides very quickly, but yeah, summarize the SEDs and see what they do when you again fit them with a modified black body, because this is all we have for the comparison. So we did this, and we see that the color temperature is, we did this so as I said, there's a degeneracy when we fit with a modified black body in temperature and beta. So what we did this in different wavelength ranges, so in the Herschel bands, in the Planck bands, in the range from 100 to 500, and in the range from 100 to 870, and see how this fit actually is comparable. But in general, we see that the temperature from the original diffuse dust model to the denser dust grains, or core mantle, and aggregates, we see that the temperature decreases, that the beta clearly increases due to the adding of this aliphatic-rich material, and that the emissivity increases. And this is exactly what was observed with Herschel and Planck when we entered the molecular clouds or the filaments. So this model might explain this well. So we didn't do in the calculations before include any radiative transfer calculations, but we did this for one case. So we formed this kind of filament where in the outer region we have the core mantle grains of the diffuse interstellar medium, then the addition of the second mantle, and eventually the formation of the aggregates in really dense filaments. And what we see is here that we find the temperature decreases while the beta increases more or less in the numbers which is observed. So this scenario might be very interesting, might be a good scenario to explain the evolution from the diffuse to the denser interstellar medium. Another thing which is really interesting is the albedo, how the albedo changes here. So we find very good, so this is for the diffuse interstellar medium. and then for the variations with a second antioxidant aggregation. So we have a very good agreement with measurements from Attila and Wittingen. And this is mainly because we see that the absorption coefficient decreases while the scattering stays more or less the same, which is really interesting. It's a very nice application as well, because what we see in this range here, from about 2 to 8 micrometer wavelength, for these core mantle grains, we see this is relatively flat, the albedo. But when we go to the core mantle grains and the aggregates, we see we get this increase here in the albedo between 2 and 8 micrometer. And this is exactly what is observed in the core shine and cloud shine. So the cloud shine, the core shine here clearly shows this shine at 3.6 and 4.5 micrometer and 5.8, while at 8 micrometer we do not see this shine anymore. And this is also seen in clouds, which is called cloud shine. So that might be one scenario which can explain the core in cloud shine, which we call sea shine. Okay, another application where the dust model is used is in this Wikipedia, where several hundreds of galaxies, SNPs of galaxies will be analyzed using the model to describe the interstellar medium of these galaxies. And then is of course the question, so we are here so far, we can, well here maybe so far, so we have like ideas that this evolution of the dust might take place in the interstellar medium. But what is happening now when we go to photodissociation regions with a particle moving apart? What will happen? So we're looking into this at the moment. And my big question, of course, is what is happening in protoplanetary disks. This is much more complicated because protoplanetary disks are much more dynamically active than in the interstellar medium. And this brings me to the next part of my talk. About the dynamical state and thus the evolution of cascading and protoplanetary disks, which are doing in collaboration with Richard Nelson in London. So, very quick introduction perhaps to protoplanetary disks, probably not really needed, but very short. So, the protoplanetary disk seen from the side is like relatively dense, very dense in the mid-plane, and less dense towards the upper layers of the disk. So that in the upper layers the radiation heats the material, while the radiation is pretty much shielded from the inside, so that the mid-plane is relatively cold here. This makes us observe protoplanetary disks in different wavelength ranges, so the cold material mid-plane is mainly observed at the long wavelength, while these warm regions here, the upper layers, are mainly observed in the mid-infrared, where we also see features and get more information from material compositions. My question is mainly what is happening to the dust particles in these regions. So how can the dust evolve? Where is the dust? In which environments here? Is it heated? Is it not heated? So on. So there are different possibilities how the dust can be transported in these disks, perhaps due to radiation pressure. This is already a question mark. Perhaps due to radiation pressure, definitively through migration and through settling and migration, but probably due to turbulences in the disk. So, as I said, this is my question: where are the dynamical behavior of dust in protoplanetary disks? So the main idea in a protoplanetary disk is that particles are settling to the midplane, migrate towards the star, where gas and dust accretes onto the protostar. That means maybe all the material that goes into the star, but the angular momentum has to be taken away from that, so we have to have an angular momentum transfer. And this was assumed to be due to magnetorotational instabilities. Magnetorotational instabilities take place when you have like a very well ionized plasma. The problem is with these disks is that they are rather cool, dense, and not really 100% ionized, so it's rather slightly ionized. So you do not have this ideal magnetohydrodynamic effects, but rather non-ideal magnetohydrodynamic effects, which are, for example, the ohmic resistivity and the polarity and the Hall effect. And these effects depend very much locally on the temperature and on the density of the disk. Until recently, there was this image that in the midplane we have a dead zone where there is no turbulences, while in the outer regions around this dead zone you have still this magnetorotational instability, so turbulences which can take the angular momentum away from the central star. But recent calculations show that it's not the case, so that the disk is rather laminar in the center, and that there's only a magnetocentrifugal wind in the upper layers of the disk, which then can take the angular momentum away. But the question is what's happening here. And this is done by two people, by Bai in 2013 and by Gressel and Ball in 2015. And this is the picture from Gressel and Ball 2015. They were using relatively simple, or at least Gressel and Ball was using relatively simple chemical reaction networks. And my idea is now to see which influence different chemical reaction networks have. So I use 3 different chemical reaction networks. And also there are different ways of calculating the ionization rate in the disk. So I also use 3 different ionization rate calculations, mainly for the X-ray, but later on also for the UV ionization in the disk. And in general, what I calculate is the L-Sasa numbers, which give me so if this number is larger than 1, then I know that turbulences are sustained. If this number is smaller than 1, then the disk is rather not turbulent. And this L-Sasa number can be calculated for these 3 different regions. So these 3 different chemical reaction networks are used. 2 of them were presented to Albedo and Nelson in 2006. This one was used in the Gressel et al. Paper. It's a relatively simple chemical reaction network, where you mainly have like light elements and heavy elements, where, as Albedo and Nelson does as well, we assume for the light elements H2, and for the heavy elements magnesium, and you have electrons. We have these 4 reactions which are taking place with these rates here shown, and so it's relatively simple, very easy. Sometimes this magnesium is replaced by HCO plus in other calculations, but it's a very relatively simple reaction network. For this other model 7 in Albedo and Nelson in 2006, they include these elements and 4 species molecules from this, so in total they have 174 gas species in this reaction network. And then they go to the THEMIS database, which gives all the chemical reactions which are possible. And with these 174 gas species, they find more than 2,000 reactions which can take place in these environments. So this is the second model I take, and this was considered in the Bai 2013 model, who also found this rather laminar disk. And the third one I use is the entire THEMIS 13 database, which has more than 6,000 reactions. So as you see already, when I do this one entire disk, so I divide my disk into tiny little cells. These calculations are extremely fast. These calculations are moderate, and these calculations take a long time. And when I make the comparison, I would like to know which one can I take, which one is really the best one. At the beginning, these calculations or these reactions do not include dust, but I also include dust in these reactions, this network, and I assume dust grains which have charges between -2 and +2. And as Albedo and Nelson does, I divided it also into mental reaction and grain reactions. So X presents like a certain gas species, and you can have like an interaction with the dust, mainly due to charge exchange in this case. And the dust and the species can go, the gas species can go on the surface of the dust particles or dissolved from the dust particles, or we have like the direct exchange, for example, of gas, electrons with dust particles, or also interactions between the dust grains. So I include these reactions for all 3 chemical reactions. This is a result from Belgium and Nelson 2006. So what they show here is the active column density. So this is the column density of the total disk. And they see this is the active one. That means here they don't take any dust particles into account. And for the dotted line here, there's dust included in this model. So this is for model 4 and model 7. And we see clearly in both cases, when the dust is included, the active column density is decreased. That means the electron abundance is much lower when the dust is included. That means the disk is less active because of the missing electrons. Really. And we see this in both models. Sorry. Yeah, here they use the Reynolds number. I always use this Elsasser number. So I get the electron abundance and I calculate the Elsasser number from this one. And if I have the limit of 1 for the Elsasser number, everything which is larger than 1 means the turbulence are sustained, and everything which is smaller, it's rather laminar. And here they use the Reynolds number, which is another number you can use for getting this limit of active or not active. They use a limit of 100, which is but for me it was mainly interesting here to see that the influence of the dust is really strong when it comes to the activeness or to the amount of electrons really. My calculations will always have the dust particles included. So it's in general lower and more dependent on the dust particles. The other thing I use is like 3 X-ray ionization rate models. So the first one is from Froment et al. It's a relatively simple one where they assume either thermal Brennstrahlen or a ring located above and below the midplane where X-ray radiation is coming towards the disk. And they do not assume any scattering of this X-ray radiation into the disk. The next one, I call it IR2, is from Bayern Goodman, and they assume the same Brennstrahlen coronal ring, but they now include the scattering of the radiation into the disk. And the last two ones are based on this quantum radiative transfer cord from Melanie Köhler, also used by Cleves et al. But they include absorption and scattering of photons. And the other thing here is also that the UV can be included, which I'm showing you later. I assume their disk model in most of the cases. I'll show this later. Just in one case, I go and reduce the dust density, counting for acetylene for the dust particles. Let's see what we get. So this is the disk I assume, so this is the density of the disk. I go up to 40 astronomical units, and the temperature distribution of the disk. So close to the midplane, close to the star, it's relatively dense, and the density decreases then also into the upper layers, and we see the temperatures here in the disk are relatively small. The results for these different reaction networks. So we see here the electron abundance. I plot for model 4, 7, and for the entire THEMIS database. And what we can see already that here the electron abundance is much smaller than in the other cases. But we can also see that they're very similar, which is really nice because we can say that we can actually use model 7 instead of the entire THEMIS database to do our calculation, which will save us a lot of time. What I plot here is the density map, which I showed in the slides before. And here is the limit of this Elsasser number, the limit of 1, where everything above here we have like still turbulences, and inside there are rather low turbulences. And this is for the different regimes and for the different models. We see the variations here for the ohmic resistivity are small, especially between the model 4 and the model THEMIS database, between those two. And for the ambipolar diffusion, they are actually the same, and also for the Hall effect, they are relatively small. So the models themselves are relatively similar, especially these two ones. And in the following, I will take this model 7, where the calculations are much bigger.
Excuse me? Sorry, the previous slide, in IR3A, I remember you said the density
No, this one not. This is the one, sorry, in the B1 it was. So this is the normal, this is exactly the disk I showed here. Okay, and now the results for the different ionization rates. So these are the ionization rates for the three different models. So this very simple one from form you clearly see there's not much radiation or going into the disk. So the ionization rate is extremely small inside the disk. So the scattering really makes a difference. What we see here, where it's the same idea, but the scattering is included, and you clearly see the higher ionization rate due to the scattering of the ionization into the disk. The surface here from this Monte Carlo calculations is relatively similar to here, while we see that the radiation cannot penetrate deeper into the disk. And when we decrease, so this is the case where we decrease the dust density, we clearly see it has an influence how well the ionization or the radiation can scatter into the disk. Here's the same picture again, the density plot with the different regimes of the Alsacer number, and we see for the very simple model, nearly everything in the entire disk is pretty much laminar. There's no UV no radiation going into the disk which can actually ionize the gas, so that there are hardly any electrons in the disk. While for the other models, especially when we reduce the density, the disk in the upper layers can be still turbulent. What is also important is the UV. Well, the first calculations were only done for the X-ray ionization, but I said in the last code I can also include the UV ionization. And this is especially important when you have dust particles, because dust particles can scatter the UV ionization, while plasma doesn't do it for the X-ray ionization. But in this case, we use the size distribution, and that means you have like the UV can actually hit the dust particle, it's scattered back, but it's also scattered forward, which is really interesting because we see here, for example, the influence. This was only due to the X-ray ionization, and we clearly see here for the UV ionization, it's really important in the upper layers of the disk how strongly this region here is ionized. And especially in the case where we reduce the dust particles by a factor of 100, we see how strong this UV radiation can penetrate into the disk and ionize the gas there. So for a case where we have actually dust settling, this might play an important role. And here are the results. Again, the disk, the density plot of the disk with the different ohmic, with the different Alsacer numbers. So for this IR3A model, so for the very normal model with a normal dust distribution, there's in general not a very big difference in this limit here. It might change, the electron abundance changed clearly here in the upper layers, but the limit is not really influenced, especially for the ohmic resistivity. Plays a little bit a different role here. But when we go to this reduced dust scenario, we have here the green line, which is without UV, and the tiny little blue line here for the with UV. That means the entire disk can become turbulent when we really have this dust settling scenario in the disk and the strong UV radiation. I said the UV radiation was calculated with the size distribution, so I was interested in how much, what is really the role of the dust particles in this scenario. So I did calculations for different sizes, only one size in this case, for 0.1 micrometer, 1 micrometer, and 10 micrometer. I kept the mass, the total mass constant, so I have to reduce the number density in each case. But I see it really makes a difference. If I assume this is a dust growth scenario here, so it really makes a difference. If I have like only small particles or only large particles, how much the UV can actually penetrate into this. So there are two cases here, the dust settling and the dust growth, which can actually make the disk more turbulent. So actually quick results I said. So the disk interior is dominated by non-ideal MHD effects, and dust settling and growth can lead to turbulences. But all the calculations were done with spherical rings, and when particles grow, they are not spherical rings, really, they are rather aggregates. And I started the calculation with aggregates, but they're still running, and I can unfortunately not show the results yet, especially for the UV penetration into the disk, it might play a role. But there are a lot of information we have that we assume that dust particles have rather these structures. So there are these experiments, there are particles we collect in the interstellar medium, and this very nice study by Kato in 2013 also shows that dust particles can stay porous until large sizes. And the last thing I want to show is like a very simple, small calculation I did. It's the settling time of the dust particles depending on the structure. So if there are spherical grains, shown here in black, if there are aggregates with a relatively porous structure, the fractal dimension of 1.8, or aggregates which are a little bit more compact with a fractal dimension of 2.5. What I also did, I varied the size of one of the monomers, or of all of the monomers, of 0.1, 1, and 10 micrometer. So here for certain masses of grains, I can see if they are spherical, they need like a certain time, but if they are porous, I can see they need much longer time for settling, which is also interesting in the scenario of settling, growth, and penetration of dust particles into the disk. And this is done for all the time region. So it's a very simple calculation, but I think it shows nicely that the settling of dust really is influenced by dust properties, if they are aggregates and how strongly, how porous they actually are. So my conclusions, the first part of my talk was about the diffuse and dense interstellar medium. So our new dust model, the THEMIS dust model, describes successfully observations, for example with Planck and Herschel, and hopefully therefore a good model for the dust in the diffuse interstellar medium. And due to dust evolution, accretion and coagulation processes, we are able to explain the observations in denser regions in the interstellar medium. And from the last part, the protoplanetary disks, I could show that disks interior are dominated by non-ideal MHD effects, only due to growth or settling turbulences can be sustained or start again. And the dust settling times depend strongly on the structure of the grains. And the plan I have for the next month to work on is mainly to publish this paper, but also to go a step further and see if we have planets in the disks which form gaps, to see how these what happens actually to the turbulences in the disks, how that's really influences the dynamics of them. Thank you very much.
Thank you, Melanie. Very nice talk. So let's open for questions. Let's see, already 1, 2. So.
Hi. I have a question about the Gaussian. So people are saying that the Gaussian is interpreted with a few micron size spherical particles, but you are saying that we can explain with the formers or aggregate. So my question is, can you constrain how large is the monomer from your calculations? Can you put some lower or upper limit on monomers?
So we use a size distribution here and also a size distribution for the monomers, therefore. But we assume that monomers about, with a maximum with a distribution maximum at 100 nanometers. So our aggregates are about 200 nanometers, more or less in size, so the maximum distribution. Yeah, they have to use these large particles because they need a strong scattering. And you know, coming from the calculations, if you want to have strong scattering at this wavelength, you need these large particles. But due to the aggregates, or due to the second mantle accretion, we get directly the strongest or the reduced absorption coefficient in these regions, and therefore the albedo increases at least by them. It's a little bit different than what they assume. But they only assume spherical particles. Yeah.
During your discussion of ionization in protoplanetary disks, you mentioned ultraviolet and X-ray, but I didn't understand what assumptions you were making about the cosmic ray ionization.
It's not included in these calculations right now.
How important do you think that's going to be in reducing your dead zones?
Yeah, so this discussion about this paper by Cleves et al., I think 2014, 2013, and she has, I think the conclusion mainly was that they are not very important in this disk, and I also take exactly her disk. I didn't try any calculations with X-ray by myself, but yeah, I don't really know.
Sorry.
So, as someone who doesn't know much about dust, the conventional line picture that we have is that it's a very diffuse sort of a process that you would generally assume at like very effective at low densities or trying to affect the light in the interstellar medium where things are not actually forming per se at very high densities of like the 5, 6, 7, 8% of the cube. Is that roughly correct?
So in the diffuse interstellar
Yeah,
medium, so
yeah.
we are much lower, so we are 22. So we have really these separated dust particles. So you do in this area you would assume very much growth.
Yeah, so my question is that when you go from this transition of 10 to the 2 to the higher intensity, like you showed the thing about free electron fractions, the ionization of hydrogen, etc. So for primordial compositions, this becomes very important for formation of like the first molecular gas cloud, etc. So at what density does this effect kind of die away or get shielded and we shouldn't care about it, and at what density it's very critical?
That's a very good question, and we don't know the exact density limits yet, because this was the model and we compared it just to scenarios, fixed scenarios. But my colleague Melanie Köhler, she's right now looking really at filaments, observations of filaments to really get, and make the model of the filament to radiative transfer calculations, where we can much more fix like the different limits of the density. Yeah.
Do you expect it to become subcritical at some point, or do you think it will keep just increasing this effect? Because
Well, it's a good question as well, because we only assume these 4 monomers. If we wanted to go to much larger aggregates, it's very difficult to calculate this. So I would assume, of course, that the denser the region, the larger the dust particles grow. But then it's more difficult to do the calculations at the moment. If we really want to assume these dust particles, this aggregate structure. So we have to find a way, and I think there are some approaches right now. We should not the paper today. So there are some approaches to perhaps that it's possible. But it's very difficult at the moment to do this calculation.
As far as I can see, your dust model does not explicitly contain PAHs. Can you comment on that? So you get the emission features you can reproduce with your aromatic metals?
No, not with the metals, but with very small grains. So they are aromatic rich, what I said. That means these dust particles are not free-flying PAHs, but the benzene rings are included in a structure of dust particles. So they are not this plain PA rings which are flying, PA particles which are flying. But these benzene rings are included in this structure, which then gives exactly the features which we see as well. So it's not like a plain PAH, but you still have the structures which can have the benzene rings. Which does them. Well, the smallest ones are 3 nanometer. Right? The smallest particles we have are 3 nanometer. So there are not that many atoms really in some of them have like still some connections, but the density rings in them. So this gives the features.
Further questions? Yeah. Yes.
In a way, I'm range of access ratio. I think the mass budget of the answer that should be different because you're increasing the affected area of your mass as you get per grid. So how does the model, how is it sensitive to the assumption of the survey?
Yeah. So what we did, I want to say why we did this actually with the spherical grains. Of course, it's because of the mean theory. We could calculate it easily with spherical grains. I did some calculations where I used DDA. And so I took a spherical grain. It was just for one single grain, for a spherical grain, and just put some of the dipoles, took away and put them somewhere else to make actually a relatively irregular structure. And I saw a small increase at long wavelength. I think it's normal also when you go to spheroids or something, you get a small increase at long wavelength. We didn't do this mainly because so I did a model before. It was mainly on if I make the aggregates or the contact area between the aggregates, between the different monomers, how this influences, for example, the absorption coefficient and so on. And the question was, so we saw when we went away from this sphericity of the grain that built like the monomers, that just going away from the spherical grains gave us already this increase. So for the aggregates, we wouldn't have any problems. Just for the dust diffuse interstellar region, where we would assume an increase at longer wavelength. We look a little bit at the polarization right now, which we clearly see as well in a little bit denser regions. And there we have to go away for the spherical grains, from the spherical grains into something more elongated or something like this. We didn't do because it was also, the problem is the calculation time again. So yeah, it's something you should keep in mind. At the beginning it was the calculation time. Yeah, it's a very good point, clearly.
Is it feasible to make a prediction for the amount of settling you need to just about trigger the turbulence? The reason why is that if if you're settling, you kick in turbulence, but turbulence will counteract settling. So the dust goes back up, that switches off the turbulence again. So I guess there must be some kind of, equilibrium just on the border. Is it feasible with your models to calculate that boundary value, how much settling you will get?
What I could try is change the density throughout, or change the density like a settling procedure or something like this. I can try this.
But these models are not so heavy that you can't.
No,
that would
so
be very
a day for one disk, so possibly.
That would be very. I would be very interested to know the answer. Are there any final questions? If not, then I would say let's thank Melanie again.